Hello guys, in today's video I want to compare the technology that we used when the man landed on the moon and the technology that we use today. So basically I just want to make today a analog versus digital technology. I want to focus on meters, multimeters that can measure voltage, current and resistance, and the calculators because those are the most important tools while designing an electronic circuit. So let's get started with simple digital equipment that we see nowadays. We turn on the multimeter and we straightly see the measurement on LCD panel. Most of the time on this meter, for example, the best resolution is 4 significant digits. When it comes to the calculator that we have here, the best accuracy is 8 significant digits. And this is the accuracy of those measurements, of those devices. So this is how digital devices nowadays work, and we are used to this, that we have numbers displayed in a number form just on a display. If we will compare it to analog device, such as an analog meter, we have a scale with divisions and we have different ranges. And based on the range that we choose, we need to know how much volts we have per division. So for example, on 10 volt per division, we will have 1 volt here, 2 volts here, 3 volts here, 4 volts here, 5, 6, 7, 8, and per division we have 0.2 volts because it goes like that: 2.2, 0.4, 0.6, 0.8, and then 3 volts. And this is how it works. On a slide rule, on the other hand, which we'll be comparing today to a calculator, we have some scales, as we can see, that are slightly graduating till the end, as we can see, and it consists of 3 parts. We have the stationary part, we have the sliding part, which we can slide, and we have multiple scales on the front, and of course a cursor to take exact measurements. The cursor is like a needle on an analog meter. So here I have prepared a small number of calculations that I want to do with a slide rule. So first of all, let's explain a bit how slide rule works. So I hope that you can see that we have different scales here on the right. It starts with a logarithm scale, cube scale, square scale, inverted scale, normal scale, sine and tangent scale. So right now, if you want to multiply numbers, we need to add 2 lengths together. So assume that we want to multiply 2 by 4. So we slide the beginning of the scale closely to 2, and then we read it of the scale. We wanted to multiply 2 by 2, so we read on the top scale 2, and under this we have 4. And this is how to do multiplication. If we want to divide 4 by 2, we need to put 2 on the top of 4 and then see where the scale begins. It begins on 2. So 4 divided by 2 is 2. So let's right now do simple calculations. 2.4 times 5.3. So we need to find 2.4. 2.4 on our scale will be here. So then we put the beginning of our scale on top of that, and then we want to multiply it by 5.3. So we can see that we are over scale because we have 5 here. So we need to reverse that, which means that we have different order of magnitude, And right now let's slide this scale on here with 10 corresponding to our thing that we want to multiply, and we want to multiply it by 5.3, so 5.1, 5.2, 5.3. So what we are reading is 1, 2, 7, 5, I would assume. And right now we have higher order of magnitude, so we have something like that. So then we want to multiply 5.5 by 3.3. So let's do 5.5, which is here, and we want to multiply it. Obviously it will be over the scale if I'll do it like that, so let's go the other way around, multiply it like that. 3.1.2.3, and it corresponds to 18.2. I think we can assume it like that. Right now we have 6.8, so we have 6.8 is roughly here, and multiplied by 2.4, it will be over the scale, so I need to position it like that. And let's do 2.4 here, read it off the bottom scale, which is 16.3 and something here like that. Then we have 9.2, which we have over here, and we want to divide it by 2. So we put 2 on top of it, exactly like that, and then we slide it here, and we have 4.6. Then we have 6.87, which is a bit more precise number. So let's find 6.8. So we have 6.5, 6.6, 6.7, 6.8, and we have like a 7, so it's almost next division. Now we want to divide it by 2. So we divide it by 2, and we move our cursor over there, and we have 3.4, and I can tell that it is 4. Then we want to divide 6.7 by 9. It will be over the scale. So we have 6.1, 0.2, 0.3, 0.5, 0.6, and 0.7, and we want to divide it by 9. And we are over the scale on this side, obviously, which is not good, obviously. So we need to do it. We have overlapping scale here, so you can see that it will be like 0.605 or something like that. So let's right now compare these two calculations took by a calculator. So we will be able to see how precise we did. So 2.4 times 5.3 equals 12.75. Bang on. Then we want to do 5.5 times 5.5 times 3.3 equals 18.15. We assumed it to be 0.2. Then what we want to do is 6.8 times 2.4 equals 16.32. So a bit bigger number than the real one. Then we have 9.2 divided by 2, 4.6, bang on. 6.87 divided by 2, 4.435. So we were pretty close. And then we have 6.7 divided by 9, which is equal to 0.744. So it's a bit off. Let's try to redo it. So let's divide 6.7 by 9. 9 doesn't fit here exactly. So let's do 6.7 here. Let's redo it with this side of the scale instead of this side of the scale that I did before. And right now we read 7.1, 7.2, 7.45, I would tell. So 745. So yeah, that's how a slide rule is compared with a calculator in 21st century. So we can see that you are still able to get sometimes two significant digits. I mean 4 significant digits. But when you compare it to a thing like that, it's like a completely different thing. Of course, there are some things that the 4 operation calculator can't do, which is, for example, it can do only square roots. Here we can do cube roots. We can do easily inverts of different numbers. We can do proportions very easily on a slide rule. We can do very simple operations on trig functions, trigonometric functions. For example, it can be easily used when you are calculating things like triangles. So we, for example, know one side of the triangle and the angle, and then you want to know what is the second side of the triangle, or you want to know what is the second angle. It's very easily doable on a slide rule and would take a bit more time to do on a calculator. So when it comes to calculations like that, I think that slide rule is a bit better. It's still a very usable thing if you want to have something that doesn't require batteries, something that is mechanical, so you can just throw it in, don't care about replacing batteries and stuff like that. And in my opinion, it is just more durable. It can fall on the floor and some other stuff, and nothing should happen with it, while a calculator can have a burned screen or a broken screen. So let's right now move to the meters and compare analog versus digital. Okay, so right now let's compare meters. So the first thing that we can tell straight away is that this one is auto ranging and this one is manual ranging. Another thing that we can tell is that here we have obviously a scale and here we have a digital display. Okay, but first thing, you need to remember the polarity on an analog meter. So if you want to check the polarity and you don't have null meter function, you need to remember that the polarity should be correct, because if not, you can make a pretty big mechanical stress on the needle, which can cause it to bend. But okay, let's connect my 10 volt power supply, and we have here 10.07, and here I think you can see it that we have slightly less than 10 volts. And it is not because parallax error, it's truly a bit less than 10 volts. So let's set this meter to be 5 volts, or maybe let's try with 9 volts. Exactly 9 volts, and we can see that it's just a bit more than 9 volts on the analog one. So let's set this one to be 8 volts. So right now we are getting closer. Nearly 8 volts, a bit higher than 8 volts actually. So let's do 7 volts. So 7 volts, nearly the same situation, a bit higher than 7 volts actually. Then we do 6 volts, which is a bit under, but still it's within the spec of the meter. What I want to show you is that you are able to do stuff with analog technology, so you can see that we can make reliable measurements. So let's right now go to 5 volt, exactly 5 volt. On this meter we are like exactly 5 volt right now, and here we are slightly less, which is okay within the spec of this meter. Let's go down to 4 volts. So we are nearly exactly 4 volts right now, and we are exactly 4 volts on analog. Let's go down to 3 volts. Right now we are exactly 3 volts, and we are exactly 3 volts on the analog scale. So let's go down to 2 volts, and on 2 volts we can see that it is actually pretty off, but when it comes to 2 volts we have much more precise scale, and on much more precise scale we have appropriate voltage. So we can see that 2.25 volt is 2.25 volt on both. 2.5 volt is actually both 2.5. 2 volts, here it is just a bit bigger than it actually should be. Here it should be 1.75 and it is 76, which is okay. 1.5, and then my power supply can't be much really precise under this voltage. So 1.5 is okay. So this is basically a comparison of these two. If I would show you a voltage that is oscillating, it is clearly visible here. And here, if I would, for example, connect a charging and discharging capacitor, and for example a 555 timer circuit, it will need to rearrange in the middle. So I will need to put it in the manual range. And when it's rearranging, changing the range, there are zeros on the display, it rearranges, it finds the correct range and stuff like that. Here we have no problem like that, and we see the needle bumping around. So really, when it comes to analog technology, it's really interesting, but this is basically the technology with which human was put on the moon. So really, if you want to try this out on your own, you can print out simple DIY slide rules online and try them out. When it comes to an analog meter, they are very cheap nowadays, so you can try them out. And in my opinion, it is just worth trying, because nowadays everything is digital, and sometimes just seeing those numbers on some kind of scale is just so charming, immersive, and I still find it useful sometimes. Analog meter is just more reliable in some situations than the digital one, and the same situations occur with cheap 4-function calculator and a slide rule. So Thanks guys for watching and see you next time.